All right. Hello, everyone, and welcome back to Psych 3510. Today's lecture is going to be over the statistical test named a single sample t-test. You'll also see this called a one sample t-test. Those terms are sort of interchangeable. There's no hard or fast rule about when you should or should not use either one. You'll see it both ways, so just keep that in mind. And I'll probably, throughout this lecture, slip sort of back and forth between the two terms. They really are quite interchangeable. So what we're going to do today is discuss um, why we have a one sample t-test, what it does, why we use it, when we use it, and then we're going to get some practice with actually doing these by hand. So without further ado, here is the formula for a one sample t-test. Don't worry, we'll break this down as we discuss when we use it and why it exists. So if you remember back to the last big chunk of work we were doing, it was on z-scores. And a z-score is all about understanding how extreme or not extreme a particular individual is, right? A single person's score is in reference to the population. So if we know Sally's IQ score, we can place Sally somewhere along a normal distribution of IQ, whether she's close to the mean, whether she's low on IQ, or whether she's high on IQ. A z-test will allow us to understand where Sally as an individual exists in the normal population. However, science is not typically done with single individuals, right? There are perhaps some rare cases in things like medicine where we might look at very particular case studies of a single person that can really teach us some interesting things. But most of the time in mainstream science and behavioral and social science, especially in psychology, we're going to be working with samples of people, right? Any one individual person doesn't teach us a whole lot about, the impact of personality on how you raise your children, right? So if that's our research question, how do aspects of personality impact child rearing? Looking at a single person doesn't tell us anything. We need to look at samples of people, 20, 30, 40, 50, 100, 200 groups of people on which we collect this data. So as we move from a z-test to a t-test, we need to keep in mind that we're now working with samples. We're working with groups. This is something that a real-life researcher might actually do. Z-tests are not super common in the literature. They exist, obviously, but most of the time, real research is done with groups of people. So a single sample t-test is something that you might actually encounter in a real scientific paper because it involves doing statistics on data from a group of people. Now, not all statistical tests are created equally. For example, there are multiple kinds of t-tests. We're just going to look at one here in this course, but you'll look at other types of t-tests in the future in 3530. So we have to know when to use particular types of tests. And the single sample t-test is built for a very particular situation. And this situation is one in where we collect data from a group of people. The number of people in our sample is signified by the letter N. Technically, a lowercase n, or what we'll often call little n, is the designation for the number of participants in a sample. Technically, a capitalized N is sort of a slightly different conceptualization of sample size, but for our purposes, right now they're just going to be interchangeable. So we're just going to call this N. N equals our number of participants in the sample, and in the situation where we use a single sample t-test, we have the mean of my sample, those people that I collected data on, and we're able to calculate their standard deviation. So the sample standard deviation, again, this S signifies the sample standard deviation. That's going to be interchangeable for us with SD as well. And we want to compare my sample to a known mean of the population. So this is kind of a bit of a rare situation. Again, it occurs, it happens. You will see these tests in the literature, but it requires us to have like a whole bunch of data at the population level on whatever variable it is that I'm studying. Meaning, um, we could use a single sample t-test when we're studying IQ because we have population level data of IQ. If we were going to study and see if a group of newborns is bigger or smaller than the average newborn, right? We could do that because we know the average length and weight of newborn babies. We have millions and millions and millions upon millions of data points. We know the population mean. So this situation is when we're comparing a small group of people, our sample, and we're seeing how they stack up against a known population mean, but we don't have the population standard deviation for whatever reason. So we're looking at a known population mean. We don't have the population standard deviation, but we have our sample mean, sample standard deviation, and obviously we know the number of participants in our sample. So we want to compare our sample to the known population. The best way to sort of learn about this and figure it out, we're going to break down this formula over here. X bar represents our sample mean. This sort of weird, funky U is a mu. That's mu. It's a Greek letter. Mu is going to represent our population mean, sort of the known population mean, like IQ is 100. So the numerator of our t-test statistic is simply a mean difference. How different is your sample from the population? Super easy, super clean. The denominator is slightly more complicated. The denominator is our sample standard deviation, that S from over here, our sample standard deviation divided by the square root of our sample size. So we want to be sure when we're doing these calculations to keep in mind order of operations, right? We want to do this square root first. That's the first calculation we'll do in this entire thing. And then we can divide S by that square root of n, and then we divide our mean difference by our denominator. So we need to keep in mind order of operations here. It'll be very important. If you don't follow order of operations, you will get this wrong every time. So let's think about conceptually what's going on here. My numerator is a mean difference. How far away from the population is the average of my group of people? Our denominator is basically serving as an estimate of the variability at the population level. So we're taking the variability that we have, right? The information on variability that we have, which comes from our sample, and we're using the sample size to estimate how much variability we should be expecting at the population level. Because the question that we want to answer is, does our group, our X bar, our sample, differ from the population more than we would expect by chance? Remember, we are convinced in science by extremity. Things that are highly likely to occur are not convincing of us, or rather do not convince us. And things that are extremely unlikely do convince us, right? Remember our coin flipping example. So if we want to know, does our sample differ from the population, then we need to know how much should we expect any random sample to differ from the population, because we need to beat, in a sense, we need to beat that expected deviation. Now, this goes back, if we think back a few weeks, to our discussion of sampling and sampling methods. We talked about a concept back then called sort of sampling error or random error. And the idea is that if I choose any random group of, let's say, 10 people, and I measure their IQ, even though I know that the average IQ is 100, it's very unlikely that the average of those 10 people is exactly 100, right? It might be 102, it might be 106, it might be 93, it might be 97.5, right? Those random 10 people are going to naturally vary around the mean. And so my sample of 10 people should approach the mean, but will not be exactly the mean. There is some amount of variability that I should expect naturally to occur when I sample a group of people. And so what our denominator does here, s divided by the square root of n, is it says, okay, given the size of my sample, how much naturally occurring variability should I expect? And then the numerator asks the question, did we beat that naturally occurring variability? Are we more variable than we should expect to occur by random chance? Because if we can't beat random chance, then nothing special is going on. So numerator is how far away is my sample from the population. Denominator is how much should we expect them to vary just normally, naturally, randomly. And so what we essentially have is a fraction of that relationship. And as t increases, right, as t gets bigger, it means that my sample differs more from the population. So a t of 2 means that my sample is closer to the population than a t of 4. And a t of 4 is closer to the population than a t of 20. So let's dive into an example and sort of learn how to work these things out along the way. So let's imagine that you are a clinical psychologist working at a university and you want to know if psychology majors are less depressed than the average college student. So are psychology majors less depressed than the average student? You know that the average student scores a 24 on the BDI. That's a real measurement of depression. It's called the Beck Depression Inventory. So you collect BDI scores from 8 of your psychology majors, and you're going to compare it to that known population average of 24. If alpha equals 0.05, do psychology majors have lower depression than the average student? So here we have our data points. We have 8 psychology majors who we've collected data from, and we need to figure out, are they less depressed than the average college student? So the first thing we want to do is define our hypotheses, the null and the alternative, or the research hypothesis. So the research hypothesis down here at the bottom, H1, is the thing we expect to happen, right? What do we think is going to happen? Well, we think that psychology majors will score less than the average college student. They will be lower on depression. So the mean of our psychology majors will be less than the mean of the population. Then we want to define our null hypothesis. The null hypothesis would be then essentially every other outcome. There are 2 other possible outcomes: that psychology majors score greater than or equal to the average college student at the population level. So my psychology majors are greater than or equal to the average college student. Keep in mind, just as we did before, that the null and the research hypothesis should be mutually exclusive, meaning that 1, they encompass all possibilities of reality, and 2, only one of them can possibly be true at the same time, right? Psychology majors are either less than the average student, or they are greater than or equal to. There is no other possibility. One of these must be the case. And remember, we start sort of conceptually, philosophically, theoretically, we start with the null hypothesis, and we only move to support the research hypothesis if the evidence and the data compel us to. So if the evidence and data compel us to move away from it, we are rejecting the null. And if the evidence do not, if our psychology majors turn out to be, let's just say, equal to the population, then we would fail to reject the null. We would stick with the null. Okay, so in this example, we were given raw data. We had the X's, right? We had the scores for every single person. But that still leaves us with some work to do, because if we go back really quickly to our formula for a t-test, we have all of our X's, right? We have all of our sample data. So we could pretty easily get a sample mean. We just take the mean of those 8 people and boom, we have our X bar. The problem gave us mu. It gave us the population mean, which was 24. That's the average college student. And we know that we have 8 people, so we already have n. So we already very quickly could fill in 3 of these terms for our t-test. The problematic term is S, right? The standard deviation of our sample. So we have some work to get this S. Thankfully, we already know how to derive S, right? From our section on variability. We know how to take raw data and turn raw data into a standard deviation. So once we do that, we will have all 4 terms that we need, and then we just do some simple math and we have our t-value. So let's do that right now. So this process is going to be getting us our standard deviation that we need for the t-test. First, we have our 8 data points and we find their mean. So it turns out the average psychology major scores 15.75 on the BDI. We take that mean and we find a deviance score for each individual, right? How far is each individual from their group mean? We square everyone's deviance score, and we get a sum of squares. Remember our best friend from a couple weeks ago. Once we have this sum of squares, we can plug it into the formula for variance. And here we have a slightly different form of formula for variance than we did previously. If you go back and flip to the slides and the examples on variability, you would see that the variance was sum of squares divided by n. But here, when we're working with a sample data and we're calculating a test statistic, a t-test, we need to divide sum of squares by n minus 1 instead of just n. N minus 1 reflects the fact that we are working with a sample and we are trying to estimate the variance in the population. Remember what we talked about back on slide number 1. We want to know how much variability should I expect to naturally occur in the population. I don't have that data. All I have is the data's mean. So I take the next best thing I have, which is the sample data, and I'm going to try and derive and estimate the population variance from my sample variance. Now, because we're using a sample variance, we will always underestimate the variability in the population if we were to just use sum of squares divided by n. Because I only have 8 participants, we recognize that this variability of my 8 psychology majors is not a perfect representation of the population, right? This is just 8 psychology majors. And so because we will always sort of not quite estimate the population correctly, we compensate for that with n minus 1. This helps us estimate the population more accurately, because a group of 8 people is more likely to vary than the population. So to deal with this underestimation, we say our denominator for variance is n minus 1 instead of just n. Now, if you don't really care that much about all that theory, just memorize, and don't forget that, on your exams, I'll be giving you these formulas, and so you just have to follow them. You should try and understand what's going on here with n minus 1. we're estimating the population. And so because of that estimation, we need n minus 1 instead of divided by n. But to do the math, you don't have to understand that. So if that doesn't quite stick right now, don't worry about it. Let's just learn the steps and learn the math, and then you can go back and try and figure out the sort of the theory behind why we need n minus 1. Okay, so here we have the sum of squares. We're going to plug and chug into this formula. Sum of squares divided by n minus 1. I had 8 participants, so 8 minus 1 is 7. So 319.48 divided by 7 gives me a sample variance of 45.64. I need the standard deviation, so I take the square root of 45.64. Remember, a variance is s squared, so s is just the square root of s squared. So we take the square root of 45.64 and it gives us 6.76. And so now we're actually ready for the t-test. We have my sample mean of 8 psychology majors who scored 15.75. We were given the population mean for all students on the Beck Depression Inventory, which was 24. We just calculated S of 6.76, and we know that we had 8 data points, so we know N. So we plug and chug 15.75 minus 24. It's very important that you always put the sample mean first. Don't flip-flop the sample and the population means. They are not interchangeable. We need to put the sample mean first in this equation, because then our sign of our t-value will reflect the directionality of change of our sample versus the population. Notice here that psychology majors are below the mean. 15.75 is less than 24. So that's going to cause this whole formula to become a negative number, right? Because the numerator is going to be negative. If our psychology majors scored greater on the BDI than our population, then the numerator would be positive and it would cause our t-value to ultimately be positive. The denominator will always be positive. There's no negativity there. If you end up with a negative denominator, you've done something wrong. Go back and check your work. But always make sure to do the sample mean minus the population mean. It must be in that order. That way, t reflects the directionality of change. So 15.75 minus 24 divided by 6.76 divided by the square root of 8. So we take the square root of 8, that's 2.83. Remember, we're always rounding to 2 decimal points no matter what we do. Every calculation, every step rounds to 2 decimal points. Get 2.83. So we go 6.76 divided by 2.83 gives me a denominator of 2.39. We take our difference score between our sample and our population mean, and that gives me negative 8.25. So negative 8.25 divided by 2.39 gives me a final t-test statistic of negative 3.45. Great. Negative 3.45. Is that big? Is that small? What should I conclude from that number? Well, we don't know yet, just like we didn't know with a chi-square. You get a chi-square value, and we need some benchmark for making our decision, right? Are we going to reject or fail to reject the null? Is this result statistically significant? Does negative 3.45 represent a large difference or a small difference? We don't know yet. For that, we need a critical value, just like we did with chi-square. This time we need to derive our critical value from a t-table because we're doing a t-test. T-tests are different from chi-squares, so our benchmarks are different. So this is what our t-table is going to look like. There's a lot of stuff going on here. Don't worry. We'll learn about it as we break it down and use it. So we need 3 pieces of information. We need what's known as degrees of freedom. We had this in chi-square. That's just n minus 1. N being the number of participants in our sample. We need alpha, which if you go back to the beginning of this problem, we defined as 0.05. And then we need this new decision. We haven't encountered this yet before. This is brand new with t-tests. We need to decide, is this a one-tailed or a two-tailed test? So, degrees of freedom is easy. N minus 1, so 8 minus 1 is 7. Our alpha was 0.05. And we have a one-tailed test. Now, one-tailed and two-tailed refers to whether or not your hypothesis has directionality. And what I mean by directionality is that, are you making a specific prediction about whether your sample will be less than or greater than the population? Did we specify a direction? Versus a two-tailed test in which we would not specify a direction. We would a two-tailed test. The language would sound something like that psychology majors would differ from the average college student. Notice how differ from, or is different from, or is different than doesn't imply directionality. You could be, if you're different from the average college student, you could be lower than them or you could be higher than them. So we need to be able to tell from our research question, that's where we derive this information. Do we have a one-tailed, a directional hypothesis, or a two-tailed, a non-directional hypothesis? I'm going to flip back really quickly to our research question. If you're a clinical psychologist working at a university and you want to know if psychology majors are less depressed, that's our key term there. Less depressed. Less depressed has directionality. Less depressed means that we anticipate our psych majors to be lower than the population average. So we have a one-tailed test. So we're going to put these three pieces of information together. And these three pieces of information are going to tell us whether or not, are going to provide us the critical value for our t, which will then serve as our benchmark for making a decision about significance. So first, we have 7 degrees of freedom. So we know that we're going to be operating on this row of 7. Now, for future reference, you can see that this table does not have an exhaustive list of degrees of freedom. Once we hit 30, it starts jumping around a little bit, 30 to 40 to 60 to 80, 100, 1,000. So if we end up with a degrees of freedom that is not on this table, let's say you had a degrees of freedom of 47, right? It's between 40 and 60. If your degrees of freedom is not exactly on this table, then you move up the table to the next number on the table. So if you had 47 degrees of freedom, you would just use the row of 40. If you had 32 degrees of freedom, you would just use the row of 30. If you had 500 degrees of freedom, you would use the row of 100. Moving up the table actually makes it more difficult for us to achieve statistical significance, and that's what we want. We want to be more conservative, right? Remember, science is a conservative process. We don't make claims unless we are certain of them, and so in cases where degrees of freedom fall off the table, we make it more difficult on ourselves by moving up the table. But anyway, back to our example. We have 7 degrees of freedom. So we know that our critical value is somewhere on this row and nowhere else on the table. We don't need to look anywhere else anymore except for this particular row. Now up here at the top, it's going to tell us which column to use. And this is where we combine our two other pieces of information. So we have a one-tailed test. So we need to identify alpha, which is 0.05, along these one-tailed numbers that are the top. If we had a two-tailed test, then we would be identifying alpha here on the second row of numbers. So we have a one-tailed test, And then we want to come over until we find our particular alpha, which was 0.05. If we had a two-tailed test and our alpha was 0.05, we would be using this column instead, right? 0.05 two-tailed. But we were 0.05 one-tailed, and so we use this column here. We look for the place where the two columns intersect, and that's our critical value, 1.895. That is our benchmark. If our observed t is more extreme than 1.895, then we will reject the null and conclude that our sample differs from the population. Notice how there are no negative numbers on this critical value table. Well, that's because the normal curve, or rather the t curve, just like the normal curve, is redundant. It is symmetrical on the left versus the right side of the curve, below versus above the mean. So because we have a one-tailed test, we know that we're going to take this value of 1.895 and we're just going to stick a negative in front of it. So our critical value actually becomes negative 1.895 because I had a negative one-tailed hypothesis, right? I thought that psychology majors would score lower than, less than the average population. Now, had I thought that psychology majors would score greater than, then I would just use 1.895. The table's already positive. I have a positive directional hypothesis, so I keep it positive. But we had a negative directional hypothesis, a one-tailed negative hypothesis, so we need to put a negative sign in front of that. Now, if you had a two-tailed test, what a two-tailed test means is that you're saying, well, I'm not sure whether the psychology majors will be greater than or less than my population. So I'm going to give myself a chance on both sides of the curve because I don't know which direction they're going to be. So what we would do in that case is we would take this value on the table and we would say, well, now our critical value is actually two critical values. It's plus or minus 1.895. But of course, we would be working from this row instead. So our critical value, if we were two-tailed, would actually be plus or minus 2.365, right? 0.05 two-tailed. Notice how if we were two-tailed, it makes our critical value larger. We would have to go from 1.895 to 2.365. This makes our hurdle higher, right? It makes it more difficult for us to achieve statistical significance. But that's because we're sort of hedging our bets by giving ourselves both sides of the curve, right? The positive and the negative side of the curve. And so because of that, we need to make it more difficult, right? If you're going to get two chances that psych majors can differ by being higher or lower, then we need to make it more difficult to keep things fair for probability, right? To keep this probability at 0.05. Okay, so we have a one-tailed negative hypothesis because we thought they would be less than. So we know our critical value is going to be negative 1.895. I always like to draw the curve. I highly recommend doing this on scratch paper as you practice these problems and for the exam. We draw a curve. Remember, these are essentially standard deviations, which is what we have with our critical value and our t, right? It's how many essentially expected standard deviations are we away from the mean. So we define our cutoff point, our critical value, which was negative 1.895. So if our psychology majors are more extreme than this point, so anything to the left of this critical value, then we would conclude that they do in fact differ from the population substantially. They are lower on depression than the average student. And so when we plot our critical value of negative 1.895 that we got from our table, and then we plot our calculated t value of negative 3.45, we see that they are in fact significantly different. They are more extreme than the cutoff, right? They're way out here in the tail of the distribution, meaning that this score, this average score of 15.45, would be very unlikely to naturally occur in our average population, right? This is a highly unlikely score. Look how low it is on the curve. And so, because this is a highly unlikely occurrence, we are convinced by it because we said, we think psychology majors are less depressed than the average student. We collected our data, and it showed that our psychology majors, if we compare them to the natural population, our psychology majors are extremely low on depression. So we're convinced, right? We made a hypothesis in a particular direction. We produced an unlikely occurrence in that direction. And so it convinces us that they are, in fact, lower on the BDI than the population. So we reject the null, and we are going to conclude that psychology majors are less depressed than the average student. Now, we're going to add one more thing to this, and that's called an effect size. An effect size tells us if the difference between our sample and population is small, medium, or large. It tells us the size of the effect. A t-test and our t-value tells us if there's a difference between the sample and population. But an effect size tells us the magnitude of that difference. Is that significant difference a small, medium, or large significant difference? The formula for effect size is super simple. We already have everything we need. We don't have to find anything else. The numerator is our mean difference. The denominator is S that we already calculated earlier, 6.76. So we just plug and chug, and it's going to give us a Cohen's d is the name of this statistic, a Cohen's d of negative 1.22. We actually don't care about the negative sign here. I know that's a little confusing because we care about it on the t-test. Sorry, you just need to learn and remember that we actually don't care too much about the directionality of our Cohen's d. We already know the directionality because our t was negative. Cohen's d is for the magnitude of the effect. So this being negative is just superfluous information. We already know that the sample is lower than the population. We're just trying to understand the magnitude of the effect. And magnitude doesn't have a directionality. Right? Magnitude is just size. So we can just sort of mentally drop this negative from our D term and interpret with these metrics. So an effect size of around 0.2 is considered a small effect. An effect size of around 0.5 is considered a medium effect. And an effect size of 0.8 or greater is considered a large effect. So here we have an extremely large effect size. This tells us that not only do our psychology majors statistically differ from the average student, but it tells us that this difference is robust. It is a large difference. It is a substantial difference. Something is really going on here that might be important, that warrants maybe more attention and more research. So we've established that psychology majors are significantly lower on depression than the average student. And we've just established that that difference is a robust, large effect. So we've really got something potentially important here. And now we need to communicate that finding to the world. So just like with chi-squares, we're going to need to be able to write a full APA-style conclusion. Just like with the chi-square, we have a very particular way and order in which we will write up and communicate this conclusion. We're going to start with introducing the test and our research question. So a single sample t-test, that's our test, was conducted to see if psychology majors score lower on the BDI than the average college student. Introduce the test and introduce the research question. Your language can vary slightly. That's fine as long as you accurately convey both of these pieces of information. Our next step is to state whether we reject or fail to reject the null. We reject the null because we had a significant difference. We reject the null. A significant difference was found between, and here, the third part, identify your groups and give their descriptive statistics. A significant difference was found between psychology majors who had a mean, we'll just use M because we can't make, it's difficult to make X bar on a keyboard. Psychology majors had a mean score of 15.75 on the BDI. They had a standard deviation, which we calculated by hand, of 6.76. The average college student had a mean of 24 on the BDI. So we're giving our descriptive statistics for our two groups, both our sample and the population. Next, we need to give our statistical statement. So we start with T because we did a T test. Paren, our degrees of freedom, which is 7 because we had 8 participants, close paren, equals negative 3.45. That's our T value, the calculated T value. We need to keep this negative here. It's important. Comma, our effect size, D equals 1.22, comma, P was less than 0.05. So this is non-negotiable. Again, it must look like this in this exact order with these exact numbers in the right place. There is no flexibility here. The rest of this, you can, as long as you're conveying the information correctly and appropriately, your language, like we talked about with chi-square, can vary a little bit. You need to include all of this information, but this statistical statement, this T statement, has to be this way every time. Note that just as with chi-square, if we are not significant, then P is less than alpha turns into NS, N.S, not significant. And lastly, our take-home message, explain this finding to a 10-year-old. Thus, psychology majors have lower depression scores than the average student. That's it. Explain it to your grandma. Psychology majors have lower depression scores than the average student. Okay. So I think I'm actually going to stop here. We're going to cut off this video so that if you need to go back and rewatch this video again, it's relatively short. So we're going to go ahead and sort of hit pause. I'm going to chop this video. And the next video is going to start up with a sort of discussion of this difference between one-tailed and two-tailed tests, since that's new for us here with t-tests. And then it's going to go on with some more practice problems where we'll get to practice this scenario, this situation, and with different scenarios and writing up APA-style conclusions. So again, if you need to go back and maybe review that whole thing of what is a single sample t-test and where does the math come from, you can go ahead and just restart this video and watch that one before you move on to video number 2, which will start with one-tailed versus two-tailed tests. Thanks, everybody, and I'll see you on the next video.